In this last part of my talk, I want to explain certain ideas of the proof of this main theorem that I explained in the second part, where it's about the implication that when we have an enlargeable spin manifold, then the two components in C plus and C minus are actually different in the space of initial data sets that satisfy the strict dominant energy condition. Well, this proof or the statement actually holds in all dimensions and also in a larger generality, then I will explain it here. Basically, it's not only about enlargeability, but also about A-hat area enlargeability, and it's also not about compactly enlargeability, but about also non-compactly enlargeability. But yeah, for the sake of brevity, I will only restrict to the case of compactly enlargeable manifolds, and I will restrict to the case where the dimension is even. In the odd case, you do a construction where you cross with a circle and then you use the statement in the even dimensional case. And well, it's not a big restriction actually to do this, to just consider the even dimensional case here. Yeah, so that was the disclaimer in the beginning. Let's now get started. Well, the proof basically consists of two constructions, and the first one is an old one. It is by Gromov and Lawson, and it was basically where this notion of enlargeability comes from, because Gromov and Lawson, they showed that these enlargeable spin manifolds do not admit positive scalar curvature metrics, and we can just use part of the construction of their proof in our proof, and so I outsourced this as a theorem which is not directly stated in their article, but it is what a part of their proof of the main theorem. So one thing that they show is the following: when we have a compactly enlargeable Riemannian manifold of even dimension, then we can choose a sequence of coverings and a sequence of complex vector bundles that are endowed with a Hermitian metric and a metric connection, such that the following two things hold. First of all, there is some twisted A-hat genus, which is given by integrating the A-hat form of the tangent bundle together with the churn form of the vector bundle, and these twisted A-hat genera, they should be non-zero for all I. And the second condition is that the curvatures of these complex vector bundles, well, that also carry the connection and the metric, that these curvatures tend to zero for I going to infinity. This is what Gromov and Lawson constructed, and and starting from this construction, they did something more to show that M cannot carry a positive scalar curvature metric. And we will also do more, but this doing more is now a bit adapted in order to show that these two components are different. So what do we do? We now assume that we have a spin manifold of even dimension, and it's endowed with an initial data set and a Hermitian vector bundle. And then we can construct what I call a hypersurface spinor bundle. And for this, we just take the classical complex spinor bundle, sigma m over m, and we double it. And well, when we double it, then certain things will happen that I explain in a minute. But first, let's state that this classical spinor bundle contains a lot of structures. It has a connection, which comes from the Civita connection of the metric. It carries a remission metric. It has a Clifford multiplication by vectors of the tension space of M. It has a grading, and well, when we double it, we get even more structure. We get an evolution that I call E0 dot. The reason for why I call this E0 dot is that, well, under a certain identification with the restriction of the spinor bundle of the manifold M bar. So when M lies inside a space-time, and when we restrict this spinor bundle of the space-time to this to the hypersurface, then this involution will be given by Clifford multiplication with the unit normal. So this is the reason why we have this name E0 dot here, but well, to follow the argument, it's not important to understand why this is called E0 dot. We just need that there's some involution, and well, I will call it E0 dot. And well, and there's also a right CL1 action that I call C1. Well, and both of these both of these come from the fact that we doubled the spinor bundle. So they are given in a certain way by they're given in terms of homomorphism that somewhat switches these two components and maybe multiplies by I in one component or something like this, or by -1. Well, and all these structures, they are compatible in a certain way. So, well, there are certain things that we would like of these structures. And, well, I don't want to go into details what compatible means here, but when you work in the field, then it should be clear what compatible could mean here. Until now, I didn't use all of the structure. I didn't use this K, for instance. I didn't use the emission vector bundle. This is about to come now. The emission vector bundle is used as follows. We twist the whole thing by E, and we get a twisted hypersurface spinor bundle. And the K is used with a canonical operator that we now define on this. And this canonical operator is, well, it's basically the twisted Dirac operator, but its zero order term is a bit changed. And namely, we subtract twice times the mean curvature, and this is multiplied with this endomorphism E0 dot that I introduced above. And this is what we subtract here. So it's the Dirac operator, but with a zero order perturbation, a zero order perturbation of the twisted Dirac operator. This is this twisted Dirac-Witten operator. Well, and since it only differs by a zero order term, there are many things that we can just take many functional analytic properties that we know of the Dirac operator that we now know for the twisted Dirac-Witten operator. Namely, it's elliptic. We know, well, I guess this needs a short calculation, that it's formally self-adjoint, and this short calculation uses a part that is hidden in this compatible up here. We know that it's odd, which also needs a part of this compatibility. And we know that it's here linear, and I could, well, do the same remark. And well, all of this gives now an unbounded self-adjoint odd operator that is a Fredholm in CL1 linear on the space of L2 sections of the twisted hypersurface Spinor bundle. Maybe I should say one word to the Dirac-Witten operator. The Dirac-Witten operator was introduced by Witten in order to prove the positive mass theorem or positive energy theorem, and for spin manifolds. And well, one central thing that he uses about this Dirac-Witten operator is that it satisfies a certain Schrödinger-Lichnerowitz type formula. So typically these formulas look as follows. You have a connection Laplacian, so you have the square of the Dirac operator or the Dirac-Witten operator on one hand side, and then you have the connection Laplacian on the other side, and then you have some curvature term on the other side. And now what Witten observed is that when you take a certain canonical connection, which is just the connection of the Spinor bundle, also adapted by a zero-order term that depends on the second fundamental form, then the curvature term is given in terms of the energy and the momentum density. And in particular, this here will be a positive operator if the dominant energy condition is strictly satisfied. Well, in our case, the formula has to be slightly adapted because we also have this twist bundle lying around, and therefore we are also getting an additional curvature term which comes from the twist bundle. But also here the conclusion holds that when we have the dominant energy condition satisfied in an even stricter sense, in the sense that it dominates this curvature term, then this Dirac-Witten operator, this twisted Dirac-Witten operator, will be a positive operator and therefore invertible. And well, since I don't want to write down this condition all the time, I give it a name. Namely, I say that the pair GK is inside the space of I larger than RE of M when this condition is satisfied. So now I define a subspace inside the space of strict dominant energy condition pairs by this condition, saying that this condition is satisfied. So now we need a bunch of results. One of them is the following. Suppose we have a path that starts and ends in this space, so where this dominant energy condition is very strictly satisfied. Then we can do a construction. We can associate to each t parameter here inside this interval. We can associate the appropriate Dirac-Witten operator. Well, there's a bit of a lie here because all these no, it's not a lie. No, let's not call it a lie. But we have this path of Dirac-Witten operators, and these define an element inside K1 in relative to the boundary. So K1 is the first K-theory class, and well, it turns out that this here is isomorphic to the integers. So it's given in terms of a certain index, which we would typically, I guess, think of as a spectral flow. Yeah, so the construction of this here is a bit involved, and this is what I wanted to say when I was talking about lie, but it's just that I'm hiding some elements here. So all these operators, they live on different spaces, technically speaking, because the metric changes, and so the bundle changes, and so also the space changes. So one needs to compensate in a certain way for this. But well, one can do this, and then one gets this K-theory class here. And this K-theory class will have certain properties. It is, for example, more or less from construction, and I said that this is kind of the spectral flow. It's additive under concatenation of paths. Then it turns out that it only depends on the base points. This is a consequence of the homotopy invariance of the index and the fact that this space of all initial data sets is convex. And the last thing is, which is not the consequence of this Schrödinger-Nerwitz type formula, is that when we can deform the path such that it lies within this space here, where the dominant energy condition is very, very strictly satisfied, then this index will be 0. And well, I already said this is a consequence of the Schrödinger-Nerwitz formula, because then all the operators here will be invertible, and therefore there is no spectral flow. So this allows for the following definition. Given two pairs, we take this K1 element that we defined below, and we call this index difference of the two initial data sets. I should maybe remark the following. So one can include the matrix inside the space of metrics inside the space of initial data sets, namely by taking the metric in the first component and taking the second component to be 0. Then there's also an index difference between these metrics, or there's an index difference between two metrics, and it is not the same as when you take the index difference of the matrix with second component 0 here. So this index difference is, although it's constructed somewhat analogously to the index difference that you maybe know from Riemannian geometry, it is something different. This is just yeah, some caveat here that you have to pay. Yeah. And in general, well, this is a mysterious object, and we know hardly anything about it, but there's one case where we can calculate it. And this is done by a certain kind of index theorem, what I call index theorem, which is the following. So suppose we have a Riemannian metric, and we look at pairs of the form G, lambda G, where lambda is a real constant that, well, can be positive or negative. Then the index difference, say lambda is positive, and then we also take care of the sign here. Then the index difference between the pair where the sign is taken to be negative and the pair where the sign is taken to be positive is precisely this twisted A-hat genus. Well, yeah, I sketched the proof here. It's probably you need to, the hard thing is to digest all the symbols here. Well, basically the idea is the following. This twisted A-hat genus is the same as the index of the twisted Dirac operator. This is by Atiyah-Singer index theorem. And well, we can view this as an integer, or it is an element in K0 of a point. Now there's a Bott isomorphism, which goes to K1 of the reals relative to the reals without the 0 point. And well, there's a certain construction of how to get from this K-theory element that is defined by the twisted Dirac operator acting on the space of L2 sections, and well, there's also this involution iota flying around that I denoted here. And when you look at this Bott isomorphism, what it does on such a representative, well, it somewhat doubles the Hilbert space. It accounts for additional symmetries that we gain via this procedure. Namely, there's an additional symmetry which would be minus C1 in this case, and there's an additional symmetry which we call E0 dot. And one of these symmetries is used as the additional symmetry that gives the one here, and the other one is used to define a path of operators. Namely, now we get a path of operators here, and it's parameterized over T, well, we add this other additional symmetry here. Well, and when you look at this, then you see that we've almost proved the thing. We just need to slightly rescale a bit. Namely, this element that I wrote down here is precisely the Dirac-Witten operator associated to a certain path, where we just have pairs of the form G, lambda G, and now in this case lambda is 2T over N. And so we now need to just rescale it a bit and restrict it, and we get precisely this index difference element that we want to have on the left-hand side. So the statement is that under the Bott isomorphism, this twisted A-hat genus is precisely this index difference between those two specific pairs. So with this index theorem and the construction of the index difference that I explained above, we can now put all the arguments together and prove the theorem in the special case that I restricted to in the beginning. Namely, we do the following. Let us assume that C plus is equal to C minus. In this case, there is a path starting from Big Bang initial data set and ending at a Big Crunch initial data set. And well, without loss of generality, we can assume that the Big Bang initial data set is given by G lambda G, and the Big Crunch initial data set is given by G minus lambda G. The reason for this is that all these Big Bang and Big Crunch initial data sets, I guess yes. So the reason is that all Big Bang and Big Crunch initial data sets, they are in the same component. So when it's path connected, then in particular, we can connect those two specific points. Yeah, now we observe that the interval is compact. So when we have the strict dominant energy condition satisfied, then it's also bounded below by a positive constant, this term here. Now we use the first construction, the one by Gromov and Lawson, and we choose an appropriate covering and a bundle out of this list of coverings and bundles that this first construction generates, where the curvature is of the twist bundle is small, namely smaller than half of this C from above here. And the other part of this statement of Gromov-Lawson was that this twisted ahead genus is non-zero. So now we can do the following. We can take this path of initial data sets and pull it back via this covering map. So like this, we get a path and of initial data sets, but it's not only a path in I larger of M tilde, but it's also a path of these very strict that satisfy this very strict dominant energy condition with respect to this curvature endomorphism. And for this reason, we know from the construction from one of these from one of these properties of the index difference that I mentioned right in this proposition after construction, that this relative index difference is zero. But on the other hand side, we have this index theorem, which says that this is precisely the same as a hat, as a twisted a hat genus, which is non-zero. So this gives the contradiction, and well, with this we have shown that our assumption that these two components are the same is not true. So that in fact these two components are different. Yes, so thank you very much for for watching these videos. I hope that that you were able to understand parts of the proof, or maybe, yeah, at least part of this statement that I wrote down in this article, that I was able to explain it maybe in a more understandable way than in the technical way that you find in the article. But in case you're interested more, I recommend to read the article, because there you can find all the details. So thank you again for watching, and yeah, I'm curious about questions that you may ask.